Now, I love this course like crazy. Too excited again. Now structure is what? Simply supported, you have a load in the center. Can you see at both ends what is theta equal to? Is it equal to 0 or not equal to 0? Are we clear? That's why mechanical engineers, how many of you did your electrical courses last time, yes or no? Yeah, you like it or you don't like it? Don't like it. Why? We need to see to believe. You see electricity? You see magnetism? Yes or no? That's why we mechanical engineers, we always get speeding tickets. Yes or no? We don't obey rules. We need to see what? To believe. 180 kilometers per hour, police stop you. Speeding ticket, okay. I agree now. Yes or no? Okay? So as mechanical engineers, we somehow have to have the sense of what? To be clear, if we lack the sense of feel, okay, we don't know our analysis is right or wrong. That's what this one is all about. Okay? Right. So now you all can see the what? See the boundary conditions already. Okay. So come back to so now is it coming back or is it not coming back? Hello? Okay. Can you put that is equal to 0? Make sense or don't make sense? Yes or no? Right? It makes sense now, right? So with this is the first time you'll see this, okay? And I would go more into depth. So what this is for, this is to determine the deflection of the structure using the elastic curve theory. So at least now you have an impression of what an elastic curve is. Okay? I'll be honest with you, why that relationship, I'll tell you now, I'm not a freaking clue. I only know what E multiplied by I is equal to D squared Y over dx squared is equal to what? Moment. Ask me to derive it, I'll tell you like that. Okay? That's me being honest. Okay? I mean, I could, but I'm not bothered. Okay? Right. Now, coming back to our buckling problem now. Okay, coming back to our buckling problem. Buckling, not bucking problem. Bucking problem. Today is bad. The comedy is unbelievable. Coming back to our buckling problem. So we have our, you need to have fun. Okay. This is so bad. Woof, woof. No, we're not stopping now. Okay. Oh man. Wait, I need a few minutes, man. Yeah, this is bad. Okay, so now I'll bring you back. I'll bring you back to this expression. Okay, so come back. Okay, so we are gonna apply. Let me copy and paste. Okay, this part. Okay. By the way, you guys got me into a bit of trouble in the course evaluation. So many of you like, oh, he's funny. Then I'm going to have a meeting with the dean. It's okay. It's okay. It's okay. So now when we apply the elastic curve, okay, we are going to do this. We're going to apply at a moment at point Q. Okay. I know what she's going to ask me, you know. We were again having fun in class. So you have EI d squared y over dx squared. Now this will become mq. Then I will write that this is d squared x over dx squared. This is equal to m at point q divided by ei. So we can write this, right, as this will be equal to minus ty over ei, right? Because over here, this is moment at point Q. So what I just did is I just did a substitution, very straightforward substitution over here. Then from here, we have an expression that states that d squared y over dx squared plus by py over, let me put the constant aside first. P over ei multiplied by y, the whole thing will be equal to 0. Okay. And then this expression over here, I'm going to call this my equation number 1. This equation over here, it is known as our homogeneous second order differential equation. Now this reminds us of our vibration again, yes or no? Right? Remember our vibration in 2Q, right? So we are going to now let, now this is small p, not capital P, okay? Is equal to square root P over what? EI. Okay. So therefore, equation number 1 becomes, now again, this is small p, yeah? So d squared y over dx squared plus by small py of small p squared y. Let me write properly first, okay? Will be equal to what? 0. And we know equation 1, you know, when you guys are doing mechanical engineering, there are two formulas, or there are two formulas, three. They're really important. Differentiation, integration, and Laplace transform. Are we clear? Okay. Any engineering problem, we have to use these three. Okay. If you're electrical, you use more, but mechanical engineers always use what? These three. Are we clear? Okay. So equation 1 parent function, we know comes from d squared y over dx squared plus by a dy over dx plus by by, the whole thing will be equal to 0. So this is the homogeneous equation. So we know if we were to solve for the roots, okay, just to quickly recall, we know that this will be equal to minus a plus or minus a squared minus by 4b divided by 2. Based on the parent function that I just shown you. Okay. So we know that a squared is equal to what? 0. Because equation number 1, what you see over here, we don't have a what? This basically is equal to what? 0. Okay. So therefore, the roots, right, will be in the imaginary domain. Now this sounds familiar, yes or no? So when is imaginary domain, the general solution will look like this. Y as a function of x, and this whole thing will be equal to minus e power minus ax over 2. Then we have a bracket c1 sine square root of a squared, or not the square root, the whole thing, but square root a squared minus 4b divided by 2 x plus by c2 cos a squared minus 4b, and then the whole thing multiplied by x divided by what? 2. Now, more or less, you can see where the pi squared is going to come in, yes or no? Right? Now we can see, now again, this is the general solution. Okay? So now we are going to take the general solution. Okay? Now we are going to take the general solution. And what we know is the term A is equal to what? 0. So therefore, y as a function of x now becomes e minus by 0, okay, bracket c1 sine, and then we're going to square root of minus 4b over 2x, okay, plus by c2 cos, okay, and we again have minus 4b over 2x. So if we were to simplify this further, in the end of the day, okay, this will be equal to c1 sine minus bx plus by c2 cos square root of minus bx. And finally, this will yield y as a function of x. This will be equal to c1 sine square root bx plus by c2 cos square root bx. Okay, because it's in the imaginary domain. So this is our equation number 2. So note, we have written earlier that b squared is equal to p squared is equal to b. So let me quickly recall. Did we write that? I can't remember now. Did we write p squared is equal to b or no? Did we write something like that? I can't remember where. So p squared over here is equal to what? B, yes or no? By looking at the parent function, right? By looking at, refer to the parent function. So we know that what? P squared is equal to B. So therefore, equation number 2 will become what? Y as a function of X. This will be equal to C1 sine Px plus by C2 cos Px. So now this is our equation 2B. Okay. And to be continued Friday. I'll see you. Are we okay? Okay. I'll see you guys, okay? I do apologize for